He's trying to echo string AI. That's why it causes me a lot of issues. But once we put a different number, you will echo perfect with
Personalized and all that. Yeah, that's good.
So questions so far?
How are you?
I'm okay.
Did you run into traffic too today?
No, I don't have traffic. I live a mile from here.
Yeah, definitely lucky.
Yeah, definitely.
Or well planned.
Yeah. So I want to continue digging into processes and ways of interacting with processes.
I looked up fork in Windows,
Oh yeah?
and it doesn't work at all. You have to use the Windows API.
Yeah, yeah. It's a Unix thing, but it will work in Sig. I don't know if it works in Cygwin actually.
I'll test it.
That's an interesting question.
I'll make one real quick and test it.
Or if it works in Bash under Windows, that would be interesting too. So we were playing with POpens before, and we used POpen, I think, to write to a command. Did we play with POpen with a read? I don't think we did. So let's POpen the date command for reading. And let's just read from that pipe and print it out inside angle brackets, and then let's just exit. So sorry? Chat. That would probably give me like 500 compile errors. So you can have one character off like that, but if you use that variable like 100 different places, you're going to get at least 100 different errors when you compile. This is why I always say go back to the very first error, right? All right, so, or have somebody like syntax check for you. So we'll open date with a POpen. We'll say we're going to open it for reading. And then we'll just use good old fgets to read from that file pointer into a character array. We'll print that out repeatedly. And it's P10 because I can never remember what my program names are, so I'm pretty sure I don't have a P10. And what am I missing? Missing something. Yeah.
Does F get spot? Oh yeah.
Wrong order. It's a little better. All right, so we'll run P10, and it tells me, you know, this is the string that I got from fgets. But this is the output of a command in Unix, right? So we ran a Unix command from inside our program. We captured the output of that, and in this case, we pulled it into a character array. And if I had done something like this, ls-l, right? We keep calling fgets inside this loop, and each time we do, our string fills up with another line of the output of ls, right? And if I wanted to do something that, say, runs through a directory and looks at all the files in there and maybe does something with those files, right, I could use POpen on ls, and I could take these file names and I could use those and open them up and print them out, and I could make something that like shows me the contents of every file in my directory. Or I could do an ls-l and find all the directories and then recursively call a function that goes into those directories and looks for more directories. And I could write a C program very easily that prints out a recursive tree of all the files in my system. So this is pretty powerful, right? We have the ability to interact with Unix commands from inside a C program. And with system, we can say run this command, okay, but it just runs. With POpen, we can say run this command and let me grab the output, or we can say run this command and I'm going to supply the input, which we did when we used this for BC, and then we sent it things like 2 plus 3, right? So what we'd really like to do is be able to run a command and do both of those things. Send it things that we want it to process and read things back that it generates. So we want two-way communication between a C program and a command. So we have most of the pieces we need for that. We have fork, which creates a clone of the process. We have various forms of exec. We did talk exec, all right. So we have various forms of exec which allow a process to change itself into something else. So we could make a fork, and that fork could execl BC, and now it's running the BC program. But then we don't have any way to communicate with it, right? So we're going to play with one more system level call, which is the pipe function. And pipe's a really simple function to use. So pipe creates a pipe that can be used for inter-process communication. That's what we're after, two processes talking to each other. And we pass this thing an array of integers containing 2 elements. And this will populate, this will do 2 things. It'll create a pipe, and pipes are single direction. And then it will fill the elements of this array as follows. Right, so it creates this virtual pipeline, and there's a file descriptor associated with each end. This end is what we read from, this end is what we write into. And the file descriptor associated with the end we read from, that number will be stored in element 0 of this array. And the descriptor that we write into, that number, that file descriptor will be stored in element 1 of this array. Yeah?
How about element 2?
There isn't an element 2, because if we declare P to have 2 elements, it's only got indexes 0 and 1. That's the index 0 thing that we'll bump into periodically. So if you try to use P bracket 2, you probably get a seg fault or gibberish. so I'm going to call this my pipe. It's an array of 2 elements. I don't know what pipe returns. I'm not going to play with that. Let's just call pipe, and we'll pass it this array called my pipe. And then let's just print out the values of my pipe and see what exactly this pipe function did. And we'll just exit right there. So we call the pipe function. It populates those 2 elements and it sets the values equal to 3 and 4. Right? This is not surprising. Because when we played with open the other day, we opened a file using the open call, right, this low-level chapter 2 function, and the file descriptor that came back was 3. And I mentioned if we did another open, it would probably come back with file descriptor 4. Well, pipe is basically opening 2 file descriptors, right, one on each end of this virtual pipeline. And so the first one was descriptor 3, the next one was descriptor 4. We don't need to know what those values are, right? We just need to have them in this array so that we can use them. So what can we do with this? Let me give you a kind of weird example. So let's push some stuff into this pipeline. So we're going to use the write function. It's going to take a file descriptor, so the end that we write into is in element 1. We're going to write the word hello, and we're going to write 5 bytes. And then let's read from the other end of the pipe. So we'll read from my pipe bracket 0, and we'll make a temporary array, and we'll read 5 bytes.
And because it reads 5 bytes, you don't need a null terminator?
Don't need a null terminator. All right, this is super duper low level binary I/O, so null terminators are for thinking monkeys. All right, so let's print out the status. And then let's print out buffer. I have to make my array bigger. All right, so what we got here, we got our original code. We're creating a pipe with 2 ends to it. We'll push 5 characters into the input side of the pipe, and then we'll read from the output side. And we'll ask to read 5 characters, and we'll save the return value in status. We'll print out the value of status. And I'm going to loop through and print out all 10 characters in our temporary array and see what they look like. And that should be our whole. All right, so we run it. We wrote 5 characters in, then we did a read, and the read command returned the number 5. Okay, read returns the number of bytes that it read. So we asked to read 5 bytes, it returned 5, everything is good. And the first 5 bytes in our array are HELLO, the thing that we wrote in. And the remainder of that array is unchanged. It's got whatever happened to be in there to start. So effectively meaningless stuff. Now, if I change my read and I say, let's read 3 characters, right? Exactly the same thing. Read return 3, that's what status is. And then the first 3 elements of that array have the first 3 things that were in the pipe. The other 2 characters are sitting in there. Nothing else got changed in our temp array. And if I were to say read 2 now, it would come back with the L and the O. So this pipe, right, you push things in here and they kind of queue up inside. And that's more or less independent of reading. You could push 100 things into here and you'd have 100 things queued up in this pipe, and then when you start reading, you start picking those off. Okay, this is something that in data structures is called a queue. It's something we'll study in winter quarter. You push things in one end, you pull them out from the other end. Think checkout line at the grocery store, right? You queue up in the back and the cashier takes
You know, a little
people.
bit like our Git car was. Because we had a big array.
Yeah. So this is what's going on with getcar, for example. You type stuff and it fills up in this buffer, this queue, and every time you call getcar, it pulls 1 character off at a time, right? And this is basically standard in, standard out, or standard in, standard out, right? This is the same thing that's going on in the bash shell. So what if I say let's read 10 bytes from this pipeline? What's it going to do? Well, I asked it to read 10 bytes, and read came back, and it returned the value 5. What does that mean? I know you asked me for 10 bytes, but I only found 5. Here they are. And it's telling me it found 5 bytes. And it filled in the first 5 elements of the array, and it didn't touch the remainders. Okay?
Why would get a question mark on 6 and 7th place?
Well, let's do this. Let's just print out our array before we do any reading and see what's in there. All right, so before we do any read, the contents of this temp array is just junk. Right, so I don't know what character that is. We can find out pretty easily, but it's just whatever happens to be in memory. After we do the read, these first 5 entries, which included 2 question marks, have been replaced with what we put in the pipeline, but this entry down in element 6 is unchanged, so it's still a question mark. But how can we find out what those question marks actually are?
Can we print it out?
Sure.
Print it again.
Out of the memory location.
Let's just print it out. So you're going to print out temp bracket index equals %C, and the %C will come from element I of temp, and then I'm going to say ASCII code equals, and I'm going to print that same element, I'm going to print it as a %D. So now we can see what those first 3 elements had nulls in them. The 4th element had a new line. The 5th element had a period, followed by a U, and then a -1, which printed out as that funny question mark, and then a 127 and 2 nulls.
Question mark is a -1.
Apparently. Makes you wonder what a -2 is. So this is just an artifact of printf. Printf, if you ask it to print a %C, and you give it something that it doesn't understand as a character, I may just do that. But that's going to vary from system to system also. But the overarching comment is it's basically whatever happens to be in memory. All right. And when we say read, if we read 5 bytes, those first 5 bytes will be filled in with whatever we had in the pipe. And if I run this again, it does different stuff. All right. Now we got a bunch of question marks beforehand. Now we've got even more. All right, so we're just kind of picking up memory contents, which is intriguing and possibly disturbing. But it looks like the negatives seem to print as question marks. All right, so this pipeline structure is really useful, right? Inside one program, it's not terribly interesting. We push things into one end, we pop things out of the other end. But if we create this pipeline and then we make a fork, this pipeline is still preserved, right? This file descriptor connects to this end, this file descriptor connects to that end. If we make a fork, we have a new process running, but if it reads from this file descriptor, it's going to read whatever goes into this pipe, which might be coming from a different process. So we can create 2 processes and have them communicate with one another. So let me get rid of all of this. So let's make a pipeline. So we're going to create the pipe. We're going to create a fork. And the child process is going to do the following. So the child's going to say, let's read, let's make a bigger array. Let's read 120 characters from the pipe. And let's just print out. Let's just print out what it reads from the pipe. Okay, if fork does not return 0, then you're the parent. So let's write into the input side of the pipe. All right, so the parent is going to say type something, it's going to wait for us to type something in, then we're going to write that into the input side of the pipe. So you're going to write into my pipe bracket 1, we're going to write from that buffer temp. How many characters do we want to write? This is a good edge question. Suppose we type hello. And we hit enter. So we just did an fgets, we typed hello and hit enter. What does temp look like? It's got HELLO, what else?
New one.
It's got a new line. What else?
Null terminator.
It's gonna have a null terminator because fgets will put a null terminator on for us. So if we want to write everything including the null terminator, we need to write 7 bytes. What's string length of this going to be equal to? 6, right? So string length counts everything except the null terminator. So it looks like we want to write string length plus 1. We could be lazy and just write 120 bytes if we wanted. So let's do that. So we'll say type something, we'll get something from standard in, we'll write all of that into the pipe, and then we'll exit.
Most of that string is going to be garbage.
Most of that's going to be garbage. So we'll type hello. We write that in the input side of the pipe. The parent exits and the child reads hello followed by a new line. And you gotta kind of take it on faith that the child is actually a separate process at this point, but you know that because we played with fork already. So we've got 2 processes sharing information through this pipeline. Now, if I write out using string length of temp into the pipe, and I say hello, and we got lucky. This was kind of cool though, because the parent exited and we actually got the bash prompt back, because the bash shell is waiting for the parent to exit. And then the child went ahead and said, hey, I just got a message from the pipe. But we're still sitting at the bash prompt here. But this is working better than I wanted it to.
That's a little unusual that that's the bash prompt.
Yeah. And it might not always happen. Or maybe it does. Ah, there, it didn't happen. So the child spoke up before we got back to bash. So we're seeing something else here which is a feature / issue, right? When you have multiple processes, things tend to be asynchronous. In a single C program, we know the exact order in which things are going to happen. If we have this statement executing, we know the statement that follows is not going to start until this statement finishes. Right? That's really important. If we say I equals 0 and then we say I equals I plus 1, we got to make sure I equals 0 before we increment it, because we really want I to be equal to 1 after that increment. Right? And if I equals I plus 1 happened first and then we said I equal to 0, we'd have chaos. Right? This happens with multi-threaded programming all the time. You can't control the order in which things are happening. So it becomes kind of the programmer's responsibility to synchronize things. All right, so we can create this pipeline internally, and we can create a new process, and that new process can still interact with that pipe. And that almost gets us where we want to be, which is being able to run a command and feed it standard in and standard out. But we need one more piece. And that's the function dupe. So dupe2 is used to duplicate a file descriptor. So dupe2 takes 2 arguments. Takes an old file descriptor and a new file descriptor. Okay, so this is pretty weird. We know that we have file descriptors called standard in and standard out. And standard in is file descriptor 0 and standard out is file descriptor 1. So here's what we can do. We create a pipe. Let's say it's going in this direction. This will be indexes 0 and 1 in whatever integer array we gave to the pipe command. So we have a file descriptor, which is this end of the pipe. Okay, we create a pipe, we make a fork. So we're on a new branch. The new branch still has access to this file descriptor. Now we say dupe2. Let's just call this P. Dupe2, let's take P bracket 0, which is how we read from this pipe. And let's copy that into file descriptor 0. Once we do this, if we try to read from standard in, it's actually going to be reading from this end of the pipe. So the dupe call lets us change what file descriptor 0 is in this case, so that instead of being whatever it was, which is usually the keyboard or maybe the input of a file if you're redirecting, file descriptor 0 is now this end of the pipeline. And we can feed things into this end of the pipeline by writing into P bracket 1, which our original branch has access to. So if this original branch says write into P bracket 1, and this forked branch tries to read from standard in, it's going to read whatever got written over here. So now we can say execl and change ourselves into a totally new process. But that new process, when it reads from standard in, will be reading whatever we put into this end of the pipeline. So now we have a totally new process running a totally new program, but we've basically connected its standard in to something that we can write to from our original branch of our process. And this is how pipes work in Bash. When you say command 1 pipe, command 2, this is what's going on underneath. Right? Command 2 is easy to run. You make a fork, you do an execl, but its standard in is normally going to be whatever standard in is. So before you do that exec, you run a dupe command that basically says, instead of taking standard in from where it is now, let's take it from this pipeline. And then the command that you're running into, you do the same thing. You make a fork, you duplicate P bracket 1, to file descriptor 1. And that says standard out is now the same as this end of the pipe. So now you do your execl. And whatever this becomes, anytime that it generates output to standard out, it's going through file descriptor 1, which is this end of the pipeline. So you've got a process running now, executing whatever you gave exec, but all the output it generates goes into this end of the pipe. And if you got something listening on the other end, that will receive that output, and now you've got two commands linked to each other through a pipe.
Is there a way to make the pipes, two pipes going both ways?
pipes are single directional, but yeah, you create 2 pipes.
So you do that before you fork?
You do that before. You make a pair of pipes, you do a set of dupes, and now you've got two-way communication. And now we can run a process, we can feed it standard in, we can read it standard out. And that process could be BC, it could be VI, it could be bash. Right, so you could put this together in the right way, and from inside your C program, you have access to a bash shell. If you want to execute a command, you just do a printf onto that file descriptor. And if you want to read the output, you just pull it in with a read. And now you've got a little slave bash process sitting inside your C program, which should be pretty cool. And can get you into all kinds of good troubles. So let's see if I've got any usable code here. What do we got here? We got a pair of pipes, read pipes and write pipes. We've got a temporary array. We're going to create 2 pipes, read pipe and write pipe. Let me see if I can draw a picture here. All right, got read pipes and write pipes. We're going to do 2. All right, I'm working up a picture of this. So, so we read from bracket 0, we write into bracket 1. Read from 0, write to 1. So that's what those 2 pipe commands do. And then we're going to fork a new branch, and we're going to do a dupe. So we're going to take write pipes bracket 0, and we're going to associate file descriptor 0 with that, which is standard in. So this will be standard in, and we're going to do read pipes bracket 1. And that'll be standard out. My arrows are backwards. And then we're gonna fork. Alright, so we create a pair of pipes, we make a fork, we do our dupe 2, and in our dupe 2 calls we basically take standard out on this child process and associate it with element 1 on the read pipes array. Standard in is element 0 on the write pipes. And we're going to exec the bash command. So this is going to be running bash. And once we say exec all bin bash, right, nothing else is going to happen. We can have the existential angst. But that print statement should never happen, right? Because exec changes the memory that's being executed, and so now this thread is going to be running bash, and so it should never do that print statement. If it does, something went wrong, so it'll give its cry there, and then it'll just exit. So this write statement will only happen in the original parent process, and it's going to write the following into write pipes bracket 1, which is right here. Oh, I did have my arrows in the correct direction. So the parent is going to write into this end of the write pipes, and since it's a pipe, that's going to come over here and it's going to pop up into this end of the pipe, which the child process is associated with standard in. So bash will receive whatever the parent writes into this side of the pipe. So we're going to write date, new line, PS, new line, 8 characters into the pipe, and then the parent's going to read from read pipes bracket 0, which is this end up here, which is getting whatever is fed into this end of the pipe, which bash is associated with standard out. So the whole setup is create a pair of pipes, make a fork, have that fork start running bash, and whatever our parent process writes into this file descriptor will go into bash, and whatever bash generates as output will be available from this end of the pipeline, and we'll just print that out as a bunch of characters. And so if we run this, we got the date and we got a PS. Let's make that a little more interesting. Let's do a PS space dash L. So there's a system status when this is happening. Bash is our original interactive shell. Here's the program that we just ran, full bash. It execled a branch to execute bash, and that bash executed the PS command. And all of that is still sitting out there right now, still running. Right? The pipe on bash is waiting for stuff to come in from the other end, and anything that it generates as standard out will get fed through that pipeline, and the main program is reading from that pipeline, waiting for stuff to be available until we exit. And then everything shuts down. All right, so I'm going to post some of this code on the usual spot on the website if you're interested in looking at it. So tomorrow we'll start project presentations for PA5, and then we'll see how long that takes. It'll take tomorrow, possibly part of Monday, possibly Tuesday. Depends how many groups we have and how many people show up. And then we'll come back, we'll wrap up some of this process stuff. We'll talk about signaling, and then we'll talk a little bit about profiling, and probably middle of next week we'll start doing some review. I'm hoping to post a synopsis of topics to study today on Canvas, but we'll go through it next week. All right, I'll see you tomorrow.